So today, in this video, I want to talk about a specific type of potential energy and a specific force that it goes with, and that's the spring force. The potential energy for so imagine you had a potential energy graph, U, which was, in fact, a potential energy, or in fact was a parabola centered on some reference position. Okay, so this is a parabola, and we could write the most general sort of parabola and say U equals one-half K times X minus XR squared. And we simply have chosen the reference height so that at a desired position, the potential energy is 0. Okay? Now this would represent a very stable kind of thing, because if you were standing over here on the left, the slope is negative, so the force would push you forward. On the other hand, if you were standing on the right, where the slope is positive, the force would push you back. The force, and if this parabola went forever, the forces would always try to push you back to the center. The force corresponding to this is going to be minus the derivative with respect to x acting on u, and that's simply equal to minus k times x minus x reference. So this force grows linearly with distance. The farther away from the reference position you are, the force is going to grow linearly. The force is 0 at equilibrium, at the reference point. That's by construction. And what you notice is if this amount is positive, so if you are to the right of the reference point, the force is negative and drives you back. On the other hand, if you are to the left of the reference position, if x is less than xr, so if this is negative, the overall force is positive and you're driven back forward. This the name given to this kind of formula for force is called Hooke's law. And this is the force for a spring. For an ideal spring that you could stretch forever, there's no limit. This is called Hooke's law. Hooke's law. Okay, and then this is the potential energy associated with springs. Okay, so the idea is as follows. If I have a spring, so you imagine you hang a mass, like so. If I were to, so it's in equilibrium, and if I were to push up, the overall, so in this case, the overall effect of gravity and the spring together is to reproduce this kind of formula. So if I were to push up on the spring, the mass is going to be accelerated down. And if I were to pull down on the spring, it's going to be accelerated up. So it's the same kind of thing where it's like that. This force law is a little trickier than some of the others that we've seen, in particular because it's not constant. It changes. The farther you go, the farther you stretch a spring, the bigger the potential energy. The more potential for motion it has. The more you stretch it out, the more motion you can get. So if you have a younger sibling and you want to get them with a rubber band, you don't just do a little pull. No, you pull it all the way back. Let them have it. So that's the idea. Okay, the bigger the stretch, the more potential energy, and the more force. The force grows linearly while the energy grows quadratically. Now, you might have noticed there's a constant here. This is called the spring constant. The units on the spring constant are newtons per meter. Newtons per meter. The spring constant determines how stiff the spring is. If you make this number large, it makes the curvature of the parabola very steep. And that means so if you have very steep walls to this parabola, a small change in x produces a large force. So K controls how stiff the spring is. Just a comment. I said this is the force for springs, but in fact, you can see that any stable equilibrium in any system is well approximated by Hooke's law. So any sort of potential energy, as long as you're near equilibrium, it's roughly a parabola, and the analysis of Hooke's law would go through. So that's a thing to think about. We can do a couple examples, and then we'll stop this video. All right. So some nice examples could be, let's imagine that we had a spring initially compressed. So let's imagine that the equilibrium or the equilibrium or reference position is here, and the spring has been compressed 3 centimeters. And let's say that the mass here weighs 1 kilogram, or has a mass of 1 kilogram. So what I would like to know is, first of all, what is and let's assume that the spring constant is 5 newtons per meter. So I would like to know what is the force on this mass as it presses against the spring. And then as the spring unwinds, what is the final velocity as the mass unwinds. Now, usually, not always, usually when you have these spring kind of problems, you can ignore friction because the spring unwinds quickly. And so it's kind of like an impulse and momentum sort of idea. If the force acts very quickly, then you can pretty much neglect friction during that brief moment. So let's just put this thing on ice, and then we don't have to worry about it, but that would be a typical kind of assumption. Unless the problem explicitly gives you numbers for coefficients of frictions and things like that, you might not need to include it. All right. So A is to find the force at the start. Okay. We expect the answer to be pointing to the right. So this would go according to K times X minus X reference. For this problem, K is 5 newtons per meter. X at the start is 3 centimeters to the left of the reference height because it was compressed. So that means I'm going to get -3 centimeters. So that's minus 0.03 meters. And I'm left with an initial force of 0.15, and it's negative, sorry. I forgot my minus sign. Sorry. There's an extra minus sign. I end up with 0.15 newtons of force at the beginning of this problem. B. Let's find the velocity final after the spring releases, and we're going to assume it just releases all of its energy into the mass, whether or not, so it's not like it's going to rattle around after the fact. Just assume it pushes and gives all its energy into the mass, nothing left behind. So in this situation, if I'm ignoring friction, then there's no work being done. And if there's no work being done, then I know that the potential energy that is initially all stored in the spring is eventually converted to kinetic energy of the mass, because the total amount of mechanical energy remains constant. So for that, I just want to say that 1/2 mass times V final squared should equal the change in potential energy, or minus the change in potential energy. So the potential energy drops, which means kinetic energy is going to rise. So that's going to be 1/2 times K times X minus X reference squared at the beginning. That's the initial potential energy. The initial potential energy gets converted wholly into kinetic energy. And I have to do some arithmetic. So that's going to say that the halves go away, and I get V final equals the square root of K over M times the amount that it shifted, so 0.03. So what mass did I choose? I apologize. 1 kilogram. Oh, it's going to be pretty weak. Everyone. Anyways, it is what it is. It's going to be the square root of, 0.03 squared. I forgot to find that. So that's going to be the square root of 5 times 0.03. Square root of 2 is 4, or square root of 4 is 2. Square root of 3 is 9. It's a lot closer to that, so I'm going to guess 2.25 or something like that times 0.03. Let me use my calculator. I'm getting tired. So I'm going to get 5 times 0.03 squared, and then take the square root of that answer. 0.03 times 5 squared equals 0.067. So, 7 centimeters a second. Not exactly a ball of fire, but this is a pretty weak spring. Okay. Other examples like this could be things like, I think there's a sapling question where you've got a car, so you have to distribute the force between all of the different shocks. And so each shock only carries 1/4 of the weight of the car. There's a kind of a nice formula. When you have springs that are in parallel versus series, there's a nice formula for combining them to get an effective spring constant. I'll leave it to you. You can read about it in the book. But if you have 2 springs that are in series, with spring constants K1 and K2, and they're in series, that means they're in a row, it turns out that the combined system, so if you were to kind of mentally shrink wrap the whole thing and view it as one giant spring, you would say that K total, the total spring constant, satisfies this kind of funny formula. 1 over K1 plus 1 over K2. So the book describes how you can derive that. What you do is you want to, because these are pushing on each other, you know that the force on K1 equals the force on K2. So the forces are the same, but they might have different amounts of displacement. And you know that the total displacement for the whole overall thing is the sum of the two displacements. And so that's how that goes. Use those facts to put together. Whereas for springs in parallel, so imagine springs in parallel pushing on something, two things if you want. In that case, because they're in parallel, they have the same displacements, but the forces might be different between the two. And then you simply add the forces, and you learn that here, if you kind of shrink wrap this whole thing, you'd say K total is K1 plus K2. So if you remember that, there's a couple sapling questions that might be easier to do. It's kind of a handy little formula for using when you have springs.